KMF is known, L is known, J is known, automatically you get some numeric value. For example, 10. 10 divided by, you will have S square, correct? X square, Y, S plus K. Okay. So this is what you are going to get the final value. In numerator, you have a one value, a numeric value. Denominator, you will get S square. It is a S into S square, this is second order equation. And with its coefficient, S with its coefficient YY plus K is the one constant. That's what this is what is final. In the exam, you may be asked, correct? So derive this this one starting from the voltage equation under the mechanical equation. Torque input supplied is going to be KMF and sorry, here we have the equation KMF here. Yeah, this is the mechanical part and this is the electrical part equation. From that you can derive two separate, but motor is finally multiplied with this. This multiplied with this will give the final this one. That's what we saw. Next one, this is for field control motor. Other one is called armature control motor. Only one difference we see is in the field control motor, when we write the mathematical model, you have inputs only V of F, correct? This is supply voltage. This is voltage you are going to apply 0 to 10 volts. This we apply 10 volts constant voltage. So if I vary this IF, this field current will vary automatically. The torque is nothing but IA is constant. So for understanding purpose, we are taken as 1. So that means the equation become Km and IF. Here IA is being 1, multiply 1 is same. So that's why we say the transfer function is nothing but the motor constant, right? The output is torque, input is current, field current. So this is motor constant, this is a transfer function or G of S for the electrical part. This output TM is given as input to the mechanical part. This is torque generated by electrical part is given as input to this one. This is my mathematical equation. This is my transfer function. Already we got it. Now here we are applying only one voltage is that in the equation, correct? This is the voltage supplied, is the voltage drop of the component. What are that? This voltage, this is VR, voltage across inductance, VL. That's what is shown, is nothing but input voltage. This is according to KVL. But if you see, yesterday I explained almost 1 hour, but anyhow for completeness again repeating, in case of armature, the field, here we are applying armature control motor means field voltage given a fixed voltage, armature voltage will vary with 0 to 10 volts, for example. In this case, there's the current IA, the IA will vary from 0 to XX amps, depending upon the resistance value. Okay, and of course, there's inductance also. Mainly, the current is controlled by, if current is varying slowly, it is controlled by resistance only. Inductor doesn't have much this one, but it is useful for creating magnetic flux, all those things. But current is concerned, it is only based on resistance. If the input voltage is not varied, if you keep it a constant voltage, this doesn't have any effect, only resistance has. So we know that IA equal to, actually IA equal to VA minus VB divided by RA square plus XL square, note down, of root. This is what correct formula. But XL equal to, note down, it is 2 pi FL, where L is the inductance value. That is my LF. LF is the inductance value. Inductance value of the field coil. This F is the input voltage. We are applying a voltage, correct? Armature voltage, that voltage frequency. Frequency of the input voltage. If it is DC voltage, we know the frequency is 0. When you apply this one, frequency is 0. That means this term will become 0. What will happen? IA equal to VA minus VB divided by root of RA square. So that can be written as, I can take the root. It is going to be IA equal to VA minus VB divided by RA. So this is what going to control. That means if I vary VA from 0 to 10 volts, then the output current IA will vary. Of course, there is a called a VB. That's what I want to complete today and go to the next this one before going to the next one. So we know that here, already I told you yesterday, if I take a DC motor, I'm just writing line sketch, correct? This is the body. Okay, so here you have the field coil. Field coil is in the body. This is the motor body. in which the field coil is arranged. We are supplying VF voltage here only. Plus minus, this is my VF. So because of the IF current is going, this coil has RF and LF. Correct? That is fixed because you know the motor is body will not move. It is with bolted. Then you have the armature. Armature is a rotating part. It is made of iron, this one, ferrous material, and it is going to enter this one, it is inside. And there's a shaft. There's a shaft coming out. This is a motor shaft. Okay. Then you have a bearing. Because motor armature cannot float. It should not touch the field coil. It should rotate inside the field. That means there will be a bearing. I can say there's a bearings, both ends support a bearing. It is like this. It has bearing this one friction C. And since the armature made of ferrous metal, it will be generally stackings. So it will have weight. So that means it has a moment of inertia J. Some books they put it I. But similarly, the friction on the bearing is called C. Some books they put a B. Some books they put KD. Any one of this value will be there, sir. So this is my armature. Armature is rotating. Please note that the armature coil, there's a coil on the armature. That coil is on the armature coil. I will show it in different color so that you will understand. This will wound over the armature core and this is come out. Brought out 2 wires. Here I am applying VA. Plus minus, because DC voltage means plus minus will be there. Okay. And there's a current IA. And this coil has RA and LA. The inductance of the armature coil are this one. Now, since the armature is rotating, now once you apply the current to the field coil, correct? We applied current to the field coil. Field coil produces magnetic flux. And magnetic flux, I'll show you in some other field magnetic flux, I'll show you in this one. So it produces a magnetic flux, something like this. Which one? The field coil, which is on the body. Okay. Similarly, we are supplying current to the armature. Armature also we are supplying over to VA. So because of that, armature also produces some. Okay, let me show black color, maybe easy. So this coil also produces. Please note that these are magnetic flux. Correct? They are invisible. They can penetrate air, all most of the non-conducting material except this one. So that is I call it phi A. The other one is called as phi F. This is nothing but phi F. Now these two magnetic fields are there because I am supplying VA and also VF. There are IF and IA. There are two magnetic fields always there. Whether it is a field control motor or armature control motor, these magnetic fields are because of magnetic interaction. Correct? The field will oppose or attract because of the armature is made to rotate. Because field coil is fixed, it cannot rotate. Armature is bearing, so armature start rotating. The magnetic force, torque is created because of repulsion or attractive forces of these two magnetic flux. So I say that torque of motor is nothing KMA multiplied by phi A and phi F. And we also know that phi A is nothing but IA and IF. These two are related to VA and VF. If I vary this, any one of this voltage, IF, IA will vary. Automatically, these two will vary. But torque is multiplication of this along with motor constant. Okay. Now, in the armature control motor alone, we are showing the equation. If you see the KVL, note down the KVL. Right? In the KVL, we are talking. This is the KVL, Kirchhoff's voltage law. According to that, VA minus VB. VA is applied voltage. We are applying here. This voltage apply constant voltage. This I am varying from 0 to 10 volts. Okay. Then VB is called as back EMF voltage. VB is called a back EMF generated in the armature coil. Why in armature coil this is created? Because armature coil is rotating inside the field coil. correct? Field coil magnet. Field coil magnet is there, which is constant, and armature coil produces pi F, pi A. That is also constant. For example, if you keep the armature voltage constant, it will also remain constant. But since the armature rotates inside, it works as a generator. Armature coil also works as a generator. That means it is going, the voltage will be induced in the armature coil. That voltage